here is called either your growth or your decay constant. And then t is still time. No, I'll get to what I'm getting at here. If you want to talk about money, then this starting amount, we're going to call it P instead of A naught, because P stands for principal, which is the amount that you start with. And A will just be the amount at the end, right? The K, which dictates how fast things are growing, is called the growth constant with money, because your money is going to grow over time. And since that's dictated by the interest rate, we're going to replace K with R and call it, well, the interest rate, right? And T is still time. But this model here will work for anything that's growing exponentially or decaying exponentially. See that K right here, if it's a positive number, you're going to have growth. And if it's a negative number, you're going to have decay. And this goes back to the pictures that we had of exponential functions. Oh, I totally messed that up. Our exponential functions, that was growth, and that was decay, right? Okay, so the reason why I'm bringing this up is because I don't have enough time to start systems of equations, and I think the next topic that I can throw in here with this, you might actually be interested in, maybe not, something called half-life. Okay, not the video game. Y'all know what half-life is? Anyone have any idea what half-life is? Do you feel like helping me explain it? It can be chemical.
Over time, it'll always, at a certain amount of time, it halves what value it currently has.
Okay, yeah. So who wants to sacrifice a piece of paper? Just one piece of paper. Oh, we got one right here. Yeah, not a crumbled one. Okay, do you remember my problem that I did where I took a piece of paper, I tore it in half, and we took that half and tore it in half? Took that half and tore it in half? Okay, certain elements on Earth do that naturally. They decay. And the best way I could describe it, I guess that would hopefully make some sense, is think about maybe you have a cup of water, and if you just leave it outside, or even in your house, over time, what's going to happen? It's going to start to evaporate, right? And the water's going to start to go away, right? And eventually, it'll be gone. If you were out there measuring it, it would take a certain amount of time for half that water to go away. So from here to here, half of the water, that would take a certain amount of time. And then it would take a certain amount of time for half of that to go away, right? Now with water, evaporation does not follow this model. But some things, it takes the same amount of time to go from one half to the next half to the next half. So one example of this, other than the water, is something called carbon-14. Carbon-14 is present in all of us. Anything that's living has carbon-14 in it. And our body has a way of converting sunlight and the things we eat into the carbon-14. And as long as we're alive, we maintain a certain level of it all the time. Okay? So here's the person. And at all times, they have a certain amount of carbon-14 in them, right? We're going to call that A naught. Right? That's how much is there. And as they live, the next day they have the same amount, same amount, same amount. But as soon as they die, this is my dead person now, okay? There, happy, dead. Okay? So what happens here is that the carbon-14 that was at this amount starts to go away. And so let's say this is the carbon-14 that was here to start with. It takes a certain amount of time for half of it to go away. So who's going to volunteer their phone right now to get onto Google and search to tell me how long it takes for carbon-14 to decay? So just look up half-life of carbon-14. I think it's 5,000 680 years or something like
5,730 years.
5,730 years. Look, everyone, that's how long it would take for half of your carbon-14 to go away. 5,730 years. So half of it would be there. Then, 5,730 years later after that, another half of it's gone. Understand? Then another 5,730 years after that, another half of it's gone. And this keeps going and going and going, right? It won't ever be completely gone, will it? There's always going to be some tiny little piece, right? No, so this is what we do. We have archaeologists that go dig up some bones somewhere, right? Hey, we found some bones. How old are they? So they go in, they grab the bone, because, you know, if it's real old, it's not going to be much left than bone, other than bone, right? So they go there, they grab the bone, and they have very precise instruments, and they're able to measure the amount of carbon-14 that's there. All right? So they measure the amount that's there, and from that, they can determine how old the bone is.
How do they know where it started?
Okay, so let's do an example of this, all right? I'm going to show you how this is. Well, I was going to do it anyway, all right? I was going to do it anyway. I'm going to keep that up there, years. This is the half-life of carbon-14. So let's say we find a bone with 2.25% of its original amount of carbon-14. How old is it? Now, your question was how do we know how much was there to begin with? Because every living thing has the same amount of it in it, the same percentage. Yes, every living thing, a tree, you, me, a dog, a cat, we all have the same ratio of carbon-14 to, there's another carbon. I'm not a biologist, but I know that we know what the initial amount's supposed to be, okay? Because what it is, it's kind of like, you know when you plug in your battery, your phone into the wall, it maintains the 100% charge, okay? Like, as soon as you unplug it, it starts dying. And then imagine we get your phone, it has 3%. We know how long, we know that it all has to have 100% because our bodies are maintaining 100% all the time. That makes sense. Like if we're alive, we're charging the carbon-14 all the time. We're plugged in.
It's like me and a dinosaur have the same.
Yes. Really? All living things. All living things have a carbon-14. All right? All right, so now, how old is this bone? All right, so how much carbon-14 was there to begin with? 100%, right? 100%. How can we write 100% and convert 100% to a decimal for me? 1, right? So I can say the amount it had initially was 1. That makes sense? That's 100%. How much was there when we found it? 0.0225. It has 0.0225, right? So I'm using this formula. This is the PERT formula, replacing replacing the P with A naught and the R with K. Is that okay? That's what we know, don't we? Do we know? So we know this, right? Check. We know this. Check. Do we know how much time it took to get from here to here? In other words, to get from all the carbon-14 to this. Do we know what the time is? 5,730. No. Time is how old the bone is, right? Do we know this, though? This K? Not yet, okay? Not yet. It's not this number, okay? We're going to use that number to get to K. All All right, but is everyone clear right now? We know what this is. When we found the bone, we know what this is. We know what this is. And we're looking for T, but we don't yet know what the decay rate is. So here's how we find K. I have to erase this. I need to find K. So here's the thing I can say about the half-life. How long does it take for half of it to go away? 5,730 years. Now that's been measured, all right? That's been measured accurately. So look at this formula. I'm going to use this formula again right now, and I'm going to write something down. You just tell me why I wrote this. Why did I write that? Oops, backwards. I wrote that wrong. That's the way I meant to write it. To say that carbon-14 has a half-life of 5,730 years means that if T is 5,730, right? If we started with an initial amount of 100%, that the ending percentage should be half of that. So see, this is half of 1 is this, right? Half of 1 is this. So it should take this long, this is T, this long to get half of your carbon-14 from an initial amount of 1. And do you notice there's only one variable in here? K? Can you solve for K? We're running out of time, so I'm going to do it quickly. I would do, at this point, the 1 doesn't matter, does it? No. I could just go natural log of 1/2 equals, what happens when I take natural log of the right side?
You do it on the left side too.
I do it on the left side and the right side. So what happens over here? You just get 5730K, right? The E and the natural log are going to go away. So on your calculator, do natural log of 1/2 or 0.5. You should get a weird number here. You should get negative 0.693147, something like that, equals 5730K. And then divide both sides by 5730. You're going to have a bunch of zeros. Negative 0.001209681 equals K. Well, here's the way it works. Do you see how we just came up with K? Okay. If somebody gives you the half-life of something, whether it be carbon-14 or some other thing, as soon as you know the half-life, you can always set it up just like this. Just put the number of years here, and you will always be able to find the K that way. Once you have the K, that K will work for that particular problem all the time. In other words, for carbon-14, we have a master formula. Here's the master formula for carbon-14. It says that A equals A naught e to the K, which is negative 0.0001209,681 T. That's our master formula right there. So do you see I have to convert the years over to get K. Once I have K, I'm in business. Now we're going to finally solve the problem and figure out how old that bone is. When we found it, how much was there at the end? When we found it? 0.0225 equals, how much was there initially? 1, so I'm not going to put it. E to the negative 0.001209681 T. And how would you solve that for T? Natural log of both sides, right? Do y'all see that this is the same problem? Okay, so I'm going to take natural log on this side. Over here, when I take natural log, I'm just going to get this big ugly thing. So natural log of 0.0225. Once I get the natural log of this, which is negative 3.794239997, I'm going to divide it by this.
I was wondering, how do you put the top number in the calculator with the t? Are you about to divide right now?
I'm going to divide just the number, not the t, just the number.
Good try, friend.
Because, yeah, I'm trying to isolate the t. So let me divide this by negative 0.0020968. I get approximately 31365. And I'm not even going to put any decimals on it because that's years. So it's about a 30,000-year-old bone.
That's young.
All right, I'm out of time. Do y'all know what Chernobyl is? You ever heard about Chernobyl in the former Soviet Union?